There is echo. Okay, just wait. Hello?
Hello?
Now it is okay.
Yeah, I think now it's fine.
Good morning, ma'am.
Hi, good evening.
It is evening or morning?
This is morning for me.
Okay.
I
Here
think
it
it's
is
evening for
night.
your side,
Yes,
right?
sir. Yes, ma'am. It is
Okay.
8 p.m.
So you are working late, so it's 8 p.m.
Yes, ma'am.
Uh-huh.
It's 8 p.m. Ma'am, our faculty advisor, Dr. Vivek Dixit, has joined.
Hi.
Hello.
Hello.
So, should I start introducing her,
Sir,
or
wait
we
for
are going to wait
two,
for
three
somebody?
minutes.
Okay.
Wait for 2, 3 minutes.
Okay.
Then we will start.
Okay.
So, Dr. Gu, you are from which city in China?
I'm from US.
Okay, so you were born in US.
No, I was born in China.
Okay, which place?
Um, it's it's not very famous from outside.
But
It's
I
it's
may know
one
the
of the
name.
southern city.
Southern city. Where?
Yeah, right. It's I'm not sure whether you know. It's not a very famous. It's small town.
Okay, okay, okay.
Yeah, yeah. I
Because
think so far I do not see other people beside Chinese know that city. Even Chinese people may not very familiar.
mm, because I did my PhD in Singapore, so I had a lot of Chinese colleagues there.
Oh, I see. I see. How many years you have been staying in Singapore?
I was there since 2005 to 2013, 8 years.
Oh, wow, that's a long time.
So I did my PhD there, then worked for some time.
I see. Which university you got your
National
PhD?
University of Singapore.
Oh, I see. That's great. A very good university.
And my supervisor was also a Chinese lady, Dr. Jiang Ning.
Oh, I see. I see. Okay. No wonder. You're probably very familiar with China.
I can understand your accent.
Oh, really?
Yeah,
Oh, I see. That's great. Yeah.
a few words I know, but accent I can easily understand.
Oh, I see. Good.
Like ni hao,
Oh.
and apparently the reply is also ni hao.
Oh, yeah, yeah. Right,
Yeah,
right. So it's mutual, right? Mutual
yeah.
hello.
Mutual help.
Mhm.
I've been to Shanghai. There I had my friend Yao in something like that.
I see. So after graduation, you go back to India to join
Yeah, I
university.
worked, then I came back to India.
How do you like? I mean, the teaching academic career in India compared with industry.
Well, both of them have their own flavor.
Okay, I see.
So you are in California.
Yeah, I'm in Northern California.
I haven't been to the mainland, but I've been to Hawaii.
Oh, I see.
Yeah.
Yeah. It's close to Bay Area actually.
Okay.
Yeah. So it's a good place. Very sunny. That's the one reason I like here.
So it's not that cold now, right?
Winter could be cold, but not that freezingly cold. Yeah, but also typically the cold temperature majorly in evening time. So in the daytime, it's quite mild.
Okay.
Yeah, so it's very comfortable. Yeah.
Okay, good. So Sutra did her journey, academic journey in 2010 at the University of Florida. And since 2012, she is with the University of California, Davis, where she is currently a professor. And her group is passionate in high performance RF, millimeter wave, and terahertz integrated circuits and systems, and its broad applications. The work done by her group have won 9 best paper awards from international conferences, including 4 times IEEE-MTTS International Microwave Symposium. She has received 2013 NSF Career Award, 2015 UC Davis Outstanding Junior Faculty Award, and 2017 and 18 consecutive uh, Qualcomm Faculty Award, and in 2019 UC Davis Chancellor Fellow, and in 2022-23 a Solid State Circuit Society Distinguished Lecturer. She is also a technical program committee member of several conferences on solid state circuits, RFIC, CICC, and ISSCC. So let me welcome Dr. Gu for a very interesting talk. Uh, and the topic is integrated circuits and systems for immersive connectivity and sensing.
Okay, thank you very much, Dr. Dixit.
Thank you.
So, do you need to recording?
Ma'am, we have started.
Okay. With your permission, we will record. If you don't permit, then I will ask him to stop the recording.
Sir, I have asked already in a mail for the recording and live streaming.
Okay.
Is it fine now?
Can I start?
Yes, ma'am. You can start.
Okay, sure. Again, thank you for the introduction and the invitation for the opportunity to give the talk. My name is Jane Gu. I would like to present integrated circuits and systems for immersive connectivity and sensing, by short ICS2. My name is Jane Gu from University of California, Davis. This is also part of Solid State Circuit Society Distinguished Lecture Program. Okay, so before start, I would like to invite you to imagine a world which beyond boundary and the limits. So a world that you are not constrained by your physical location. You can go to a place, meet with a person in the whole world immediately. You do not need to change your position, and also with full of experience including all the senses of human nature, human senses, including taste, touch, smell, besides normal sight and the hearing. A new world that a person is a center of his or her world, where people can seamlessly switch between different scenarios, from workplace to school, to shopping stores, to exercise gyms, etc., without even moving your position. A new world that cancer or tumor is even unheard of, because we as a human master our body inside out, down to each single organ or cell, so that we can make sure they operate at optimum condition without going to abnormal situation. So this kind of sci-fi like world is very exciting, full of opportunities and potential. To reach there, certainly we need many technology breakthroughs and innovations. One of the key requirements is the immersive connectivity and sensing. And to enable immersive connectivity and sensing, 3 pillars are must.
Sorry to disturb
Wireline.
Ma'am. Hello, ma'am.
Hello?
Sorry to disturb you, ma'am. Your slide is not like it is in a one plane, so it is not slideshow. So it is fixed.
Interesting. Okay, thank you for letting me know. Do you see my window? Right now I do not show the slide. So what do you see now? Could you tell me?
But we can see the screen. Your in a one plane, every slides are there. 9 slides are there. So it is not in a slideshow form.
Right now I do not put slideshow. Okay, let me try again. Sorry for the stop sharing. Share. Let me share my entire screen to see. It does not allow me to share entire screen. Share a window. So do you see my slide with the title World Beyond Boundaries and Limits?
Yes, ma'am. Now can you change the slide number?
I change the slide to next. Immersive connectivity and sensing.
It is not changing.
It's not changing. Still no changing?
Yes, ma'am. It is fixed on the second slide.
That's interesting. I do not have very experience how to debug in this situation. Any suggestions?
You can use the file itself without going to the presentation mode.
I can use what? Could you?
The PPT file itself. The PowerPoint file itself you can use and make the screen big basically. Just pull it down so that it becomes big enough.
Oh, you mean do not go to present mode?
Yes.
Oh, really? That will work? Okay, let me see. So you see my slides, right?
Yes.
Okay, so let me scroll down. The second slide.
Yes.
Now it is.
Third.
Now it's okay.
Now it is.
Okay. Okay, that will work. Thank you. Okay, so maybe I just start from here. Okay. So 3 pillars is a must to enable immersive connectivity and sensing. Wireline is the backbone of connectivity. Sensing is the interface between physical world and digital virtual world. Wireless communication and radar are the frontiers of connectivity. So we need significant advancements in all the 3 pillars to allow us to realize the immersive connectivity and sensing. So therefore, I will present the work in my group and also some work with collaborators in each of these 3 categories. So first is wireline communication. Particularly, my group interested in relatively short distance wireline, which we call Interconnect. And then we actually has been working on very special interconnect, which is called terahertz interconnect. Depends on the frequency definition. You could call it sub-terahertz, right? Because different people may follow different terahertz frequency definition. So I will explain why we are passionate in this frequency range. So this slide shows, the left side shows the data generation over the time. The top one shows the overall data generation. So it increased significantly, as we can see. The bottom one shows the real-time data generation, which the line, the orange line, shows the percentage. So we can see the percentage also increase over the time. So that means it increased in a faster pace. So the message from this is very clear. To support the increasing data, we need higher speed. And in Interconnect, there are special concerns in this aspects, because Interconnect typically constrained by the device physical dimension. So instead of just targeting the data rate, the most key spec is bandwidth density. So basically, the unit space data rate it can support. Okay, so that's one critical spec. The second is energy. So on the right figure shows the electricity usage in data centers from 2010 all the way projected to 2030 in 3 scenarios. Worst case means highest energy consumption, typical case, and best case. So if we just check typical case, show in the middle, the red line, by 2030, the electricity usage will be about 3,000 terawatt hours. What does that mean? So today, the entire US yearly electricity consumption is about 4,000 terawatt hours. So that means by 2030, only the data center energy consumption will take about 3/4 of entire United States consumption, which is not sustainable for 2 reasons. One, as we know that when temperature increase, it will increase, when power increase, it will increase temperature. And then when the device working in high temperature, the performance drops significantly. So it defeats the purpose that we want to have higher data rate, wider bandwidth. And the second is more fundamental, is that the power generation or energy generation of the entire world over the time is saturated, it's almost constant. So that means we do not have more energy to support the increasing needs. Okay. So the message is very clear. As a researcher in this field, we really need to work out approaches which can provide sustainability in the long run, right, so that we can continuously meet our needs. And in this slide, the left side shows the three key metrics for interconnect. Besides what I just mentioned, the bandwidth density, normally defined as gigabit per second per micron, energy efficiency, picojoule per bit. The third metric is the cost, which is apparent, right? Because if the cost do not keep dropping, very soon we cannot afford the increasing data, right? So that's very clear. And on the right shows a figure that comes from DARPA PIPES program a few years ago. This figure shows the figure of merit for wireline versus the link distance, so the interconnect distance. The figure of merit defined as bandwidth density versus energy efficiency, divided by energy efficiency. So the higher, the better. And we can see that it has two segments. The blue line, which is electrical interconnect, and the dominant short distance scenario. The white line on the bottom is optical interconnect, so it's more suitable for long distance link. And we can also see that for the blue line, the figure of merit drops significantly versus link distance. So this is due to the channel constraint. For the optical interconnect, it's not that sensitive to link distance, as we can see. And we can see there is a big gap around the meter range, where both electrical and optical interconnects are facing great challenges to address. Okay, so this is due to the features of these two interconnect. For electrical interconnect, we know that it comes from the mainstream process, so it enjoying benefits of all the mainstream process bring. And also, the semiconductor technology advancements is so much that the device speed approaching 2 terahertz. All this give the benefits for electrical interconnect. The bottleneck is the lossy and the bandwidth limited channel. So that's the reason it becomes harder to reach longer distance for electrical interconnect. For optical interconnect, it's opposite. So it enjoys extremely low loss and high bandwidth fiber, right? So it can support very high data rate and also for very long distance. And it's now the great advancements in silicon photonics and the 3D packaging also makes the optical interconnect advancements greatly recently. But still, the optical interconnect is not as cost effective compared with electrical interconnect due to complex fabrication requirements, due to its environment sensitivity. Okay, so the message here is that both electrical interconnect and optical interconnect are hard to completely address the interconnect issues, particularly the most challenging meter range scenario. Therefore, we are working in terahertz interconnect for a long time, about 10 years. The reason is we see that terahertz interconnect, due to its unique spectrum position, it can leverage the advantages on both sides. It can use the mainstream process so that it enjoying all the benefits from mainstream semiconductor process. It can also use quasi-optical channel like fiber to have low loss wide bandwidth channels. So that by combining these two, we think that terahertz interconnect has the potential to address the very challenging meter range scenario to complement existing electrical interconnect and optical interconnect. And this unique architecture will provide potential advantages for terahertz interconnect as follows. First, it's based on mainstream process. So therefore, it scales with electronic devices to support wide bandwidth, right, for high data rates with low cost and high reliability. And it leverages low loss channels similar to optical fibers so that it can mitigate link budget for high energy efficiency. And also because the channel has wide bandwidth and small size due to the shorter wavelengths of terahertz. Therefore, it provides also high bandwidth density. So it can address all the three key metrics. And on the right shows the comparison of electrical interconnect, of terahertz interconnect compared with optical and the electrical interconnect in 5 aspects. Besides the 3 that I just mentioned, the 3 key metrics, here I add 2 more. One is latency, one is bit error rate. So for latency and the bit error rate, they are application dependent. So different application may have different requirements. Okay. So for example, for memory access, especially high performance computer architecture, the memory access require both low latency and the low bit error rate. Right? For some applications such as artificial intelligence, it has strengthened the requirement on latency, but it can tolerate higher bit error rate. Okay, so and this comparison radar chart shows that terahertz interconnect can complement electrical and optical interconnects, especially to address the meter range scenario. And this slide shows our first terahertz interconnect channel demonstration. So the gray part is the channel. Do you see my cursor?
Yes.
Okay, very good. So the gray part is the channel. We use high resistivity silicon as the material to build the channel so that it can provide low loss. And at the same time, it has embedded high bandwidth feature. And the figure here shows the field propagation from one port to the other in HFS. And we also do all kinds of design optimization. One of it we can see is the S21 versus the radius size. The radius is shown here that we can see that when the radius increase, the S21 improve, the loss reduce. Okay.
Is it of copper, ma'am? Kyun, ma'am, is it of copper? This white color, what we can say, waveguide is sort of. Is it a copper or which metal, or is it dielectric?
So this is the waveguide is dielectric. The waveguide is dielectric, and
Okay, what sort of material is dielectric?
the coupler is metal. In this case, is gold.
Okay,
So
okay.
yeah. And then here I want to point out two things. One is the loss partition. So if you check this figure, we actually partition the loss along the entire structure. And the largest loss come from the coupler loss. So it has 2.6 dB from each side. But the channel loss is quite affordable, so that's the reason it can extend to longer distance. And then the figure here shows measurement results of S parameter. For example, the S21, the minimum loss is about 8.4 dB, okay? And one thing I want to highlight is the 3 dB bandwidth. The 3 dB bandwidth in this case is 12.6 gigahertz, which is not very high, right? The reason is because it's constrained by this coupler. The coupler is it's like patch antenna type. Okay, so it has very limited bandwidth, so it's constrained by that. And then the next version, we aim to enhance the bandwidth. And we call this prototype as far field. The reason is the channel has some distance to the coupler, which is in contrast with next prototype. So this is next prototype, which we call near field. In this prototype, the channel sit directly on top of the microstrip line. So there's no gap, okay, between the two. And this design, as you can see, the center is dielectric waveguide. The two sides, the yellow line, right, those are microstrip line. And we can see the electrical field transition from quasi-TM on the microstrip line, gradually migrate to dielectric waveguide mode. In this case, is EY11 mode. And because of the wideband matching, the bandwidth certainly is pretty wide. And the S parameter measured shown here, the blue curve is measurement results, the red curve is simulation. So we can see in this scenario, the bandwidth is expanded to 59 gigahertz for 3 dB bandwidth. The insertion loss is also smaller. It's about 4 dB. So that provides a wider bandwidth compared with the previous prototype. Okay. Okay, besides passive channel, as we know that the active system is the other critical part. So for active systems, it's challenging to design active circuits in high frequency, especially beyond 100 gigahertz. So in order to address those challenges, for example, the device capability constraint, the prosthetics, the model inaccuracy, so we need to do very careful design. So here, our approach is we do the co-design of all the devices together, okay, including passive, active, layout, everything, when we optimize the design. So use this conventional oscillator as an example. So for example, we want to optimize a terahertz oscillator for our interconnect. And then first, we need to identify our design goal. In terahertz interconnect, two specs are important. One is output power. The second is efficiency. So we multiply these two specs together to create our optimization objective. figure of merit. And then we sweep the device size, and then we check the figure of merit, which is the red curve, right? And the blue curve shows the optimum resistance for this for each device size. And then say we see this around the 12 micron, it has maximum figure of merit, and then we need to match with passive. So therefore, we convert into we connect to transformer, right?
How we are deciding neta here? Kyun ma'am, how we are deciding neta here in the FOM? Like, what are the parameters which are deciding it?
So we sweeping the device width, okay, and then we do the sweeping. What do you mean by parameter?
Yes, the parameter which is made by FOM, na, like the power P out into the neta sign. How we can define that? What are the factors they are defining into the second parameter of the FOM? Like one is the power out, and what is the other that neta sign there, na? So how we can? What are the factors they are defining onto that?
He's talking about eta subscript A.
Yeah, eta is the efficiency of this oscillator. Is that your question? So the power efficiency.
Yes, ma'am. So eta would be like, what are the factors are defining onto that particular eta?
So power efficiency, typically we use the power it generates divided by the power consumption, right? That's the efficiency definition. Is that your question?
Okay, yeah, ma'am. Yeah. I thought eta was defining on some sort of pattern. Please proceed, ma'am.
Okay, so then we need to make the impedance transition, and then in this case we use transformer as the transition. So when we optimize the transformer, there are two aspects we need to optimize. They have trade-offs. One is minimum insertion loss. The other one is the impedance boosting factor, right? So the design parameter is the coupling coefficient K, coupling ratio K, okay? And then we combine the minimum insertion loss into the figure of merit to realize the whole oscillator optimization, okay? And then we redo the sweeping. And this is just shows a general example of how we do the design, how we do the co-design with both active and passive. And it may take several iterations, okay? And certainly different design, different circuits, we have different figure of merit, right? Because the key spec may different, okay? And this is just to show the comparison with state of the arts. I think I need to speed up. So by short, through the holistic co-design, we actually achieve the highest efficiency, which is about 26% with the output power of 0.66 dBm. Okay, even today, I think we still hold the record for this high frequency, which is beyond 150 gigahertz in silicon process. And then we combine this oscillator with a passive switch to realize OOK transmitter. The reason we choose passive switch to implement the modulator is because the key aspect for terahertz interconnect is the efficiency, right? So we do not want to consume power for this. So that's the reason we use passive switch. And then the signal goes through the channel and reach to the receiver side. On the receiver side, we use non-coherent detection. And this lists some of the spec. We achieve about 12 gigabit per second with error-free. So that means at least the beta rate less than 10 to 0.12, okay? And the record efficiency is 0.32 picojoule per bit, which still hold today as far as we know, okay? And this is the comparison table of the transmitter with state-of-the-art, right? And also the measurement results of output power efficiency versus supply voltage. Because the modulator adopts passive switch, so it has loss. So therefore, the efficiency and the output power of the transmitter will be lower than terahertz oscillator. Okay, so in this case, if the highest efficiency is about 10%. Okay, which is still a good number at this frequency. To further support higher bandwidth density, we also explore channel multiplexing. So basically, we want to combine different virtual channels and let them transmit through the same physical link. By doing this, certainly it increases the bandwidth density, but at the same time, it mitigates the dispersion requirements for each channel. Okay, so which is a great benefit for wide bandwidth systems. One approach is to design this awesome mode channel. So basically, we utilize the EY11 and the EX11 modes to transmit two channels. These two modes are naturally orthogonal to each other. Okay, so it can realize good isolation. The figure on the left shows the awesome mode channel, and we can see some of the design pictures. The right figure shows the measurement results of this awesome mode channel. Both channels have bandwidths higher than 58 gigahertz, and the insertion loss better than 7 dB. Okay? And the isolation between the two channels is larger than 20 dB. Okay, so we also combine this awesome mode channel with active systems as shown in the bottom package here. So the left side is transmitter, right side is receiver, and then we do the testing of the system level. The combined data rate is about 16 gigabit per second. Okay, and because it will have some interference, right, due to the design non-idealities. And later on, we develop another system which is based on the frequency division. So in this demo, we combine two frequency channels into the same physical link. So one is working on 140 gigahertz, one is 180 gigahertz. And we use this couple line-based duplexer to separate and combine the two channels on the two sides. And the figure here shows the S parameter of the duplexer. And the combined data rate is 22.6 gigabit per second, and energy efficiency is 1.58 picojoule per bit. And move forward, we want to combine. We want to combine more channels into the same link, right? So we are investigating another method called mode multiplexing. And in this prototype, we have demonstrated 3 modes combined together to transmit the data. And in this demonstration, we have demonstrated aggregate data rate about 65 gigabit per second. the energy efficiency is about 1.6 picojoule per bit. And this is the first time that people show more than 3 channels, more than 3 channels through one physical link. So we think this is a great direction, new direction, to really can materialize the multi-job scalable interconnect to eventually close the long-standing interconnect gap. Okay, so next is terahertz sensing. So for sensing, we are increasingly rely on sensing, right, in many aspects of our life, from biomedical sensing, chemical sensing, Industry 4.0, etc., to IoT. So this increasing immersive interconnection with the world and continually growingness, right, drives high performance ubiquitous sensing and actuation with very stringent requirements. Okay, so those requirements include high resolution, precision without ambiguity, high reliability and robustness, low cost, low power consumption, right, easy to deploy, and also prefer to have the interoperability among heterogeneous networks. Okay, so these requirements are quite tight, right? So we need to see what are the approaches we have. Today, the labor-free sensors are investigated intensively due to the easy operation, fast response, low cost, etc. For optical side, it has investigated over decades. The sensing types, including fiber-based sensing, microtoroid, microspheroid, so those kind of sensor, they can provide very good resolution, so very sensitive. But optical sensor has the constraint that it rely on very bulky benchtop requirement. For example, the tunable laser, the optical signal processor, etc. So it prevents them to apply in our daily life usage. It only constrained in the lab facilities. Okay? For electronic sensor, it's opposite. We can use mainstream process to develop very low cost sensors, right? But the constraint is the performance is not quite yet to be able to really apply in critical life scenarios. So the question is, could we combine advantages from both sides? Right? So the figure on the left shows the performance. This in this case is a dielectric constant sensor. So we can see for the electronic sensor, which is the blue dots, has the resolution about down to 10 to minus 3 around. The optical sensor, which can have the resolution about 10 to minus 7. So it's at least a 3 order difference, right? So how can we combine the two together so that we can meet all the requirements that I stated before, right? So this question motivates us to investigate terahertz sensing because, as we know, it's unique spectrum positions between optical and microwave spectrum. And therefore, we have investigated this micro ring resonator. This ring resonator, silicon ring resonator, which is similar concept as micro ring resonator. And it has its resonant frequency. The frequency is certainly determined by the dimension, the material, dielectric constant, etc. And it also need to determine the quality factor. So we do all kinds of design to optimize the sensor. And this slide shows the measurement results of the ring resonator sensor as well as the pictures. As you can see, this is the ring sensor picture, and the figures here shows the measurement results. This sensor is basically benchtop filter type, right? So when it has different material on top, it will shift the resonant frequency. And in this particular sensor, we achieve 10 to minus 6 dielectric constant resolution, which is quite good in electronic sensors. And this is just the passive itself. And then to build the self-contained sensor, we also developed the active systems together with the passive sensor. So this is the second prototype. So this is also based on the micron ring, but we have made some adjustment. So instead of band stop, this is a band pass system. And we have, we put active systems, transmitter and receiver on the two sides to complete the sensor system. And the figure here shows the packaging. It's a bit too small to see. So in this system, we have demonstrated 10 to minus 4 resolution. Okay, so still it has a good significant difference from the optical sensor. So how can we improve, right? So the improvement, basically, we should investigate down to bottom to improve the resolution. The resolution is the minimum detectable signal divided by sensitivity, right? We either increase sensitivity or reduce the minimum detectable signal or do both, right? So for electronic sensor, the sensitivity is not as good as optical sensor due to the low quality factor. That's the feature of the device in electronics systems. So we need to working on to lower the detectable signal, right? The detectable signal is determined by system noise, okay? So currently we are investigating noise processing so that we can address those key noise components, contributors, including phase noise, flick noise, thermal noise, environment shifting, etc. Okay, we see great potential that the terahertz sensors can have similar resolution as optical sensor, while certainly we are enjoying all the benefits from the electronic side. Okay. Okay, so the last but not least is the wireless network, right? As we are start to enjoying the 5G wireless network, people already begin to work on 6G and beyond. The figure here shows the spec comparison between the expected 6G and beyond compared with the existing 5G. The 5G spec is in the center, the blue region. And we can see that almost, actually, it's every single aspect. The 6G has significant larger requirement than 5G, right? For example, let's say the peak data rate for 5G is 20 gigabit per second. For 6G, larger than 1 terabit per second. So it's more than 50 times difference, right? For the network efficiency, 5G 1 times, 6G 100 times. So it's 2 orders of magnitude difference, okay? So the question is how to meet those extreme requirements, right? What tools, what resource we have, right? So we have 3 fundamental, finite, but non-storable resources, okay? Spectrum, space, and the time, right? Spectrum is easy to understand. Now, in our low frequency, right, the single-digit gigahertz frequency range, the spectrum is very congested. To transmit higher data rate, we need to rely on more complex system. We need to use higher order modulation. We need require higher SNR, etc. Right? So the energy efficiency and the cost keep increasing. And even worse, it cause larger interference in that spectrum domain. And in higher band, for example, beyond 100 gigahertz, it's almost minimum usage, right? It's extremely underutilized. And to leverage, to be able to fully utilize spectrum resource, then the device preferred to have the capability to access the whole spectrum range. So I call the full spectrum system. The space resource, nowadays we are relying on beamforming, right, to partition the space so that we can leverage the space resource. For low frequency, it's constrained by the device size because low frequency has larger antenna size. Therefore, the array, if it can be built, cannot be very big. So the beamforming size is relatively large, right? So that's the constraint on the low frequency. High frequency is beneficial to build a large array, but the freest loss is much higher, right, in high frequency. So therefore, it's more suitable for short distance scenario, such as urban scenario or indoor conditions. In those scenarios, we know that refraction multipass situation is more complicated, which will deteriorate space filtering. So the difficulty is there. If we really want to utilize space resource efficiently, I think the device need to somehow working beyond physical limitations, right? It need to be able to sync devices, distribution located, and also probably across heterogeneous networks. The third one is time. Time is not only a spec, a requirement. For example, we always want things to be fast, right? Low latency. It's also a resource, right? So our system is preferred to be able to leverage the time resource so that it not only meet our spec, our quality of service requirement, but also can balance our system, our network traffic, so that it minimizes those rush hours, right? Minimize the imbalancing, okay? But the time resource does not get enough attention yet today, okay? But I do believe that the time awareness system with proper time resource allocation capabilities is very important in our future systems. So by all means, the three finite fundamental non-restorable resource are the ones that we can rely on. So then the question is, what are the technologies that we have to allow us to utilize those resources, right? So here list some hardware technologies that it can help to utilize one or more resources. And I will not go through them. You can read them. Besides resource, certainly the expense is another constraint. We need to minimize the expense, including the energy and the cost, right? So next, I will quickly go through some of the work in my group and also with collaborators in the wireless systems. So first is we call the error feedback transmitter. So the left figure shows conventional feedback transmitter, which has good feature that it's working very low burst. But the downside is it has the trade-off between linearity and the noise. The reason comes from the attenuation. This attenuation will amplify the noise from this feedback path. Okay, so that make the noise performance is worse. Okay, and then in order to mitigate this attenuation effect, the attenuation number, we introduce a reference path here to cancel the signal from the output so that only the nonlinearity, in this case, the IP3, the third order intermodulation, will feedback. So by doing this, we can highly mitigate the attenuation numbers here so that the noise of those systems will not be magnified significantly, so that we can optimize the performance in different way. I mean, separately, not coupled, by remove the trade-off. Okay, so that's the basic concept. The signal cancellation between the reference path and the coupling signal, conventionally, normally we would think it requires very good mismatch, right, to realize the signal cancellation. However, the good thing is, due to the loop effect, actually the mismatch requirement is quite loose. Okay, I would like you bring your attention to the figure here. So this is the signal attenuation versus the amplitude and the phase mismatch. So the amplitude mismatch can lose to -20% to 100%. The phase mismatch can lose to ±60 degrees to achieve 20 dB signal cancellation, which is enough for our system. And this shows the measurement results of this transmitter. Yeah, it really achieved a very good balance between the noise, which is about -132 dBm per hertz, and also the linearity, which we achieve the OP1 dB, 21 dBm, is very close to the PSAT. So it can show that the system reached to its maximum capabilities with also good efficiency here. A filter is a critical component in wireless communication. So M-pass filter is very active topic for the past decade due to the very high Q response and also wide tunable frequency range. So we also investigate several M-pass filter structures. In this project, we actually add 2 additional zeros to the conventional M-pass filter, so that we can notch down the nearby blockers, and the two nearby zeros can also be adjusted, so that we can adaptively to adjust the notch down. To adjust the frequency to notch down the nearby interference. So this shows the performance and also the comparison tables with state of the art. The second M-pass filter related work is shown here. We want to give more design freedom to this M-pass filter. For example, change filter type between Butterworth and the Chebyshev. And also we can play the design parameters, the capacitor, the transconductance, to adjust the in-band ripple for the Chebyshev filters. Again, we can see that this really works fine and demonstrate
Ma'am, which technology we deploy in order to create the GM1?
So we can play, so we majorly adjust the GM2 and the GM3. Okay.
So which technology, like which technology we deploy in order to get the G?
So this is a 65 nanotechnology, CMOS.
Okay.
Okay. Okay. Filter again. M-pass filter is good for high quality factors, so it can provide very sharp filtering, but it's not good to provide broadband bandwidth, right? So therefore, to make the bandwidth tunable, we actually working on another tuning scheme. We purposely introduce negative resistance so that we can adjust the quality factor. Therefore, the bandwidth can be adjusted. Okay, so this work demonstrate the fractional bandwidth tunability, as we can see in this figure. The fractional bandwidth tune between 1.5%, so very narrow, to 67%, so very wide band. Yeah, this is, to our knowledge, is the widest fractional bandwidth tunability demonstrated. Okay. Okay. Next is, as we know, phase array is important, right, for beamforming, and to ensure great beamforming performance, we need to make that each cell in the phase array has uniform performance. Therefore, we need to adjust the amplitude. We need to adjust the phase of each element. Okay. So this work is aiming to adjust the amplitude. It uses attenuator to finely adjust output signal strength. Okay, so this has achieved about 32 dB tuning range, and also the frequency working from DC all the way to 32 gigahertz. And all the detailed spec, you can see here, we achieve 0.255 LSB tuning step. Okay. And this slide shows the phase shifter for phase array, as I mentioned. And we use both electrical tuning by tuning the capacitor, and also magnetic tuning by tuning the inductor. Okay, and we use 3-stage, eventually combined together, achieve the complete 360-degree phase shifting. So that means we can shift to any place we want. Okay. It also demonstrates a good noise figure, 4.2 dB, and the center frequency is 35 gigahertz. And to support wide bandwidth phase array, we need true time delay, right? And the on-chip true time delay, especially long true time delay, is very challenging because it has large loss, consume large area, and also the frequency is quite constrained. So in this work, we have some idea that to combine the 4 transformers, as you can see from the bottom figure, into one transformer footprint, so that it can significantly lower the chip area. At the same time, it can reduce the loss and increase the bandwidth. And we demonstrate up to 800 picosecond true time delay, which to our knowledge is the longest true time delay on chip. Another factor which constrain the array element performance uniformity is the temperature. Especially for large array, the temperature is not same for different cells, and those will affect performance, right? So it will lower the main lobe gain, it will increase the side lobes, etc. And then to avoid that, we also develop this closed loop temperature compensation scheme, so that it can automatically adjust the circuit performance to improve the uniformity across the large array. And the demonstrated performance shown here, that we can see it has quite stable performance versus the temperature, right? So gain variation is 0.005 dB per Celsius. Noise figure is 0.016 dB, and IP3 also 0.022 dB. So it's quite stable, okay, over temperatures. And this shows the multi-beam system. As we know, it's important for MIMOs. So this work is 4-element, 8-beam receiver. And in this case, we do not, we have demonstrated 4 beams together, as shown in this figure. The reason that to bring 8 beams, it has too much couplings between beam between adjacent beams. Therefore, we decide to bring alternative beams to come out. Okay, so that's a consensus for the that's a practical consensus for the packaging. Okay, this slide lists our selective prior minimal wave terahertz work, all in CMOS. So it includes amplifiers, terahertz generators, synthesizers, wireless communication, passive imaging, active imaging, radar, phase array imaging, etc. Okay. So in wireless network, I think it's really a resource and expense management game. So the resource, as I mentioned, has three fundamental resources: spectrum, space, and the time. We need to maximize those resources usage. At the same time, we need to save the expense, right? We need to minimize expense, the energy, and also the mining cost. Also, we need to minimize so-called waste. In this case, for example, interference, right? When we have more users, it will cause more interference. To reduce the system complexity, we want to minimize interference. Okay, so those are our goals. To help us achieve those goals, we need great technology advancements, breakthroughs, and including some ideas or some directions that I think will be extremely helpful. For example, as I said, the system need to operate across the entire spectrum, from low frequency to millimeter wave to terahertz, even to optical side, right? And also need to be adaptively, autonomously adjustable. And the system need to interoperate through heterogeneous networks, for example, radar and the communications, right? And the devices has the capability to realize spatial computing, no matter it's synchronously or asynchronously, so that it can utilize the space resource, right? And the system need to have interference awareness and resilience capability. So it need such kind of methodology and architecture, right, to address interference scenarios. And we need to do holistic co-design across layers to maximize energy efficiency, reduce cost, right? And also all the systems need to have great security, sustainability, scalability, right? Especially with the exploding data seas, etc. So you can see those directions are very challenging, and we cannot just rely on the advancements of one single or individual fields. Okay, in order to meet those requirements, to develop those very challenging systems, we need in concert, intimate collaborations across field, list here, but not limited to the field list here, okay? So that we can really maximize the usage of the resources, at the same time reduce the waste and reduce the expense. Okay, conclusion, moving forward, situation is even challenging because we are in post Moore's Law era. We're facing exploding sea, but with limited resources. We also see hard limit power war. We do not have extra power or energy to spare, okay? So those great challenges need to be addressed, by continuous technology advancements in all the three pillars, right? Wireless communication, wireline, and sensing, so that we can realize sustainable, scalable, smart, secure, immersive connectivity and sensing to materialize our future bright world, right? As I mentioned in the first slide. So this acknowledgement is from my former and the current lab members, especially the ones listed here, my collaborators, as well as the funding supporters. Thank you very much. Small advertisement. So my group has openings for PhD and postdoctors. If you are interested or if you know someone interested, feel free to contact me. Thank you. I'm very happy to answer your questions.
Thank you, ma'am. Thank you for your information. Questions? Anyone have? Ma'am, I have one question. Like,
Yeah.
in a 8 simultaneous beamforming network, is the like you have tested with the beamformings, or it's just a simulated?
Which one?
And the slide title 8 simultaneous beamforming.
Oh, so both of the figure are matching results.
42. Yes. These are the
Yeah.
fabricated measured result.
Both are matching results.
Okay. And these are designed for at which frequency?
So it's 7.5 to 9 gigahertz.
Okay. Thank you, ma'am.
Sure.
Ma'am, this said Pankaj from IIT Jammu. So in one of your slides, like 8 simultaneous beam forming. So in that particular steps, like what sort of substrate we are deploying in that? Kyun ma'am?
What? Could you repeat your question? What?
Yeah, yes, ma'am. Actually, in one of your slides in the 8 simultaneous beam forming. So in that particular step, what sort of substrate we are deploying there
Oh,
in order to create
substrate.
that beam forming? Yeah.
So we just use a CMOS,
Okay,
process.
okay.
So it's silicon substrate.
Okay. Is it pure silicon or like it would be some sort of mixing
pure-
in that
pure-
or doping in that?
Pure silicon.
Okay, Q ma'am. Okay.
Mhm.
Anyone has any other questions? I think, ma'am, now we have concluded. Thank you for that.
Okay, thank you everyone for attending my talk. I know it's very late. I hope you enjoy your evening.
Thank you once again, ma'am, for accepting our invitation for inviting